What we're going to do today is we're going to talk about various algorithms in STL, and we're going to start by talking about remove. So here's an example where we've got a built-in array with, looks like about 8 elements, and we go ahead and we print the array to the output using our little idiom that we often use, where we can go ahead and print stuff out. Let me make the screen a little bigger so it's easier to see. There we go. And then what we go ahead and we do is we go through this range from beginning to end. Keep in mind, this is an array of built-in ints. It's not a container of anything like that. So we go through here and we remove anything that matches the value 20. And what comes back is a pointer that corresponds to the new end of this range. And what it's actually doing, and we'll take a look at the code here in a second, is actually just going through the array, one element at a time, and every time it finds something that doesn't match what you're looking for, it copies it. And whenever it finds something that it is what you're looking for, it ignores it. It copies over it, basically. And so the elements that are being removed are basically copied over by pulling the items down from right to left to overwrite the stuff that's being removed. So when you're all done, assuming that there are things to remove, and we have in this case several things to remove, what we'll end up doing is we'll end up giving back a new end iterator that points to the one past the new end, and everything that's in the beginning to up to that point does not include the value we're trying to remove. What occurs after that, it's an implementation issue, but basically it's just the stuff that was copied from before. So after it removes this stuff, we take the new end, we write things out. You shouldn't see any 20s. But if we go and copy from beginning to the end of the original range, you'll see, as we take a look at this in a second, that there's actually some stuff left over there. Yeah, question?
So, I guess I moved over the other, the removed values to the, I guess, past the end of the NN, or I guess past what NN is.
So let's tell you what, let's go take a look. Let's go take a look at the code. Anybody here ever see the movie Conan the Barbarian? It's kind of a classic. It's back when Arnold Schwarzenegger had muscles and stuff like that. And it had James Earl Jones. It had a lot of people. Had a lot of interesting actors and actresses in it. At any rate, there's this one great scene where I think it's Conan's father is giving little Conan a lesson in life. There's a couple of classic lines in the movie, but one of them is his father's basically saying, his father's a swords maker. He says, you know, there are many things in life you can't trust. You can't trust, you know, men or women or beasts, but steel you can trust. And that's one of the main themes of the movie, the riddle of steel. And anyway, code you can trust, right? You can't trust documentation. You can't trust people's memory, but code you can trust. Unless you work with Eric Snowden, and then that's a different story altogether. Okay, so let's go ahead and write and run this piece of code here. Whoops. Oh, there we go. Yeah. Okay, so you can see what it does. It prints out the original array, prints out the array that removes all the 20s, and then it prints out the original range back to the end. And you can see that there's some weird stuff at the end, including a 20. So let's go take a look at the code and actually see what remove is doing, and I think it'll help you to understand what it's doing. Go here, take a look. Here's the remove method, and it does a couple of things. As usual, you have to kind of hunt around for a while. Here's the actual implementation of remove. It goes from beginning to end of the range, and if the value that you're looking for doesn't match the one that you're currently at, in other words, it's not what you're trying to remove, you say, hey, that looks great. Let's go ahead and copy that guy over. So we copy that guy over into the output iterator that we're trying to do here. And when we're all done, then we go ahead and return that. And that is the new iterator to the new end of the range. So this next iterator, which we're writing into, only advances if you don't match. So what you do, if you do match, is we just skip over you. So that's basically what remove looks like. So what it's doing when it's all done is it's returning the iterator that's one past the end of the range that doesn't have any of the items in that we asked to have removed. As is almost always the case in STL, the algorithms are ridiculously simple. They're just a couple lines of code. So as you can see, when we remove this, we get back a new iterator, and then when we print the value out, it didn't have any 20s in it, but the original range does. And that just says don't go to the end of the range. Only go to the end of the new range. Don't go to the end of the old range. The other thing to note, and it doesn't really show up here because we're using a built-in array, if you were calling remove on something like a string or a vector or some other type of data structure, then what you would get back would be the end iterator. And you would then have to go and say to the original container, erase the things you don't want, which are basically from the end of the new range to the end of the old range. Erase those elements. And the reason that you have to do these things as two separate entities is because remove is a generic function. So it doesn't care what it's actually working on. It doesn't know or care whether it's working on built-in array or a vector that's a user-defined standard type or something you define, like an AQ or an LQ or whatever. It has no idea what it's actually working on. So as a result, it doesn't know how to actually get rid of the rest of the stuff. It doesn't know how to erase things. All it knows how to do is copy them down. So you have to rely on the container to get rid of the items by erasing them if you need to.
After you call remove, what does size of my int?
The question is, after you call remove, what does size of my ints? Well, those things are constants. Size of my ints is a constant. What that's doing, that's a very interesting question. So my ints is a built-in array, and so size of my ints is 1, 2, 3, 4, 5, 6, 7, 8 times size of int. So let's say ints are 4 bytes, so that's going to be 32 bytes. And so that won't change. That's a compile time constant. That doesn't change. So there is no change to that. Other questions?
Let's see. So pn would be.
Pend is still pend.
Right, so once you've done remove, if you set it between begin and end, it would be 10, 30, 30, 10, 10.
Well, what'll happen when we ran this example, take a look at what it does. What it's going to print out at the end is just the stuff here. This is stuff that was not copied over. See, this is what's actually active, 10, 30, 30, 10, 10. And then 10, 10, 20 is what was left here. Those were the things that were copied down from. And they're really no longer considered to be part of the active range once we've removed them. All right, so that's remove. Here's RemoveIf. As is often the case, what RemoveIf does is it simply gives you a way of being able to have a predicate. In this particular case, what you see is we have a method called isOdd, and isOdd checks to see whether or not something's odd. Yeah?
So I'm confused. Were we copying the data that we didn't remove into a new array?
No, we were simply, if you didn't want something to be there anymore, you would simply grab the thing next to it and overwrite over it. And so the old one would have its destructor called, if it had a destructor. If it doesn't have a destructor, nothing happens. It just gets overwritten. And that's how we get rid of stuff. We just overwrite it. So here's a case where we have the isOdd operator, which goes through and checks to see if something's odd. So what we do here is we go through 1, 2, 3, 4, 5, 6, 7, 8, 9, and we remove everything that's odd. And when we print this out, of course, we'll just have even numbers left because we remove everything that's odd. And this is just making the point that you can have a predicate, which is just a functor that will check to see whether something matches a particular condition. In this case, we're checking to see whether a number passed into it is odd or not. This particular example uses a functor, but there's other things that you could do. So let's go ahead and take a look at this, and we'll look at this code. Let's see. Let me go ahead and do it in Visual Studio so we can kind of peek inside the implementation a little bit, see what's going on under the hood. That requires copying a couple things, so we can copy the isOdd functor. Let's go ahead and compile this thing. Hopefully it'll run. Yep. All right, let's try that again. All right, so you can see what it has in there are just even numbers, which is what we expected. if you take a look at RemoveIf, let's go see if we can find RemoveIf. So here's RemoveIf. What RemoveIf does is it looks almost identical to what we had before. The difference is we don't compare against a particular value. We check to see whether a unary predicate or a unary functor is going to return true or false. So if it's true, then we're going to remove anything that returns true. And you'll see that idiom is used over and over and over again in STL. A couple other things that are interesting here. We could also replace the use of the is-odd functor with a Boolean function called is-odd. And we'll just spell it a little different so it doesn't have a conflicting signature. So we could now use this, and instead of calling is-odd as a anonymous object, we could pass in the is-odd pointer to function. And if the stars are aligned, you get the same result. And that, of course, is because a function and a structure class that has operator function call defined on it has the same signature from the point of view of what's expected by this template parameter. As long as you can make it look like a function, it'll be treated like that by the compiler. It's kind of this is called signature-based type equivalence, sometimes known as the duck test. If it walks like a duck and quacks like a duck, it's a duck, right? So if you can call it with function call syntax and it compiles, then it's a function, even though it may actually be an object or a functor. Yeah?
Is there any, is one better from the other?
Good question. We'll talk more about functors later, so I'll withhold giving the long answer. The shorter answer is that functors are objects, so if there's a need to hold state or there's a need to be inlined, they can be inlined and hold state. So there's a whole bunch of virtues that come from using functors. You'll see that STL uses functors very, very heavily for almost all the generic programs. And it's used, of course, for things like predicates, too, as we use it here. Yeah?
I'm not really sure how that statement which signs the end generator works. What is size of
Oh, this thing here? Yeah, sorry, let me make it a little bigger so you can read it. Let's see. All right, I think you can probably see that, right? So you're asking, what is this gobbledygook? Okay, so what we're trying to do is we're trying to figure out what's the end of this range. So we know what the beginning is. The beginning is known as pbegin, which is just the address of my ints, which is the array, right? And now we want to be able to figure out one past the end. So what we're doing here is we're simply saying my ints, or we could have said pbegin here, plus size of my ints divided by size of star my ints. And this is why C++ programmers make more money than Visual Basic programmers, right? Because they actually know what this means. Whereas Visual Basic is so simple, anybody could use it. So size of my ints, what is that? Size of is a compile time operator built into the compiler. It returns the number of bytes taken up by that particular type. So in this case, my ints is a data type that has, in this case, I think, what? 9 ints. So that would be 9 times whatever size of int is. Let's say that's 9 times 4. So that's going to be 36. So we got 36 bytes. But we don't want bytes. We want elements. So then we divide by the size of whatever an element is, which in this case would be an int. So it's 36 divided by 4, which equals 9. So now when we say my ints plus 9, that gives you one past the end. That's pointer arithmetic in C or C++.
I assume you could, instead of just using asterisk my ints, you could also use my ints and then bracket any element.
Yeah.
It wouldn't matter.
Yeah, there's various things you can do. That's kind of the generic way of doing it. Now, that code is kind of ugly, right? So you normally wouldn't write code like this unless for some strange reason you got renditioned and were forced to go to a place where they made you write C code and there was no abstraction. You'd use this kind of stuff. But seriously, most people would write STL. They wouldn't use this. I'm just showing you this to illustrate that these algorithms work just as nicely for built-in arrays of things as they do on containers of things. Okay, The next algorithm is my absolute all-time favorite. Yes?
Like the built-in array in STL has begin and end, right?
The built-in vector
Or vector.
has begin and end, which give you back iterators. And so in this particular case, that's a good question. So let's go ahead and illustrate that point. Thank you for bringing that up. Let's go back over here. And what we're going to do now is we're going to replace my ints with something different. Let's go ahead and say hash include vector. And let's change this to standard vector int. And let's call this thing my ints, just for sake of consistency. And we'll see in a second how cool C++. This is actually not going to be cool, so we're going to have to play some tricks here. I tell you, let's be cool. Let's go use a real compiler that supports C++11 syntax. Okay. Oh, look, we already had a vector. Must have known ahead of time we're going to do this. All right. Give me a second to format all this thing before I decolorize it so you can read it. Oops. Thank you. That's called, by the way, that's called pair programming. Just want you to know that. So it's the agile technique of pair programming. All right. So we're going to go ahead and compile this using C++11 syntax. So let's go ahead and say standard vector int iterator begin equal myints begin, p begin, and we'll say standard vector int iterator p end. Instead of this gobbledygook here, we'll do this. And now we can do this. Let's go ahead and say standard vector int iterator end. Well, let's call it, we'll just keep p end just to be consistent with the other one. All right, so we go ahead and look this thing up. And that should probably work if all goes according to plan. Let's go ahead and compile this thing. I'll decolorize it so you can actually see what I'm doing. G++. All right. Always nice to get things to compile the first time. So you can see it prints stuff out. So what we did here is we replaced the low-level gobbledygook using built-in arrays with nice vectors. But the bulk of the program was pretty much identical. The only difference was, as I think you alluded to, instead of using that strange pointer arithmetic to find the beginning and the end of the range, instead we simply used the convenience methods begin and end, which are simply factories that return the iterators, just like you're doing in your programming assignment. In fact, we could use this with your programming assignment if we so chose. Yeah?
Did anything you add there, was anything specific to C++11? Where
Oh, the only thing I added in C++11 was initializing my ints vector using a built-in initializer list. That was the only thing. That's a C++11 feature. If I don't compile with that, then I think I will get the compiler to yell at me. Yeah.
Is there a way to have the end iterator, or like the standard, if you return .end iterator to point to the result of remove or removeIf, or would that be something you have to implement within the as part of your container class? As in, if you wanted to do removeIf, then you didn't want to have to say this pn. You wanted to removeIf and then have it immediately point to.
Oh, sure. We could say, are you asking this like standard vector int end? You know, just make a new one. Is that what you're asking?
Could we assign myints apostrophe s myints .end iterator to what the result to what end is right now, without having a special function in the container class.
Do you mean?
Basically, to modify the container class's .end iterator with the .end iterator returns to the result of nn, or the result of removeIf, without so you can plan a special container function to do that. That would be easy.
Yeah, I'm trying to understand the use case. So you're trying to modify the way that the end factory works.
So,
And
so if you use remove and then use standard copy, you could just do, instead of having p begin p end, you could just do
Oh, I see. Well, okay. Here's what you need to do. If I understand what you're doing, this is what you want to be able to do. This is kind of what I was saying before. What we could then do is we could then say something like this. My ints erase n end p end. So what that does, I think that's what you were trying to do. What that does is that goes ahead and modifies the underlying container so that those elements are now removed. And now if you were to say begin and end again, it would give you the smaller range. I think that's what you're trying to do.
Okay. And that'd be built into the vector class. That makes sense.
Erase is built into the vector class. That's correct, yeah.
If you had an empty or a vector of the same size, and you replaced, let's say you had like another beginning iterator, would it be like a copy and remove type?
So sorry, what's the?
So instead of p begin, being
Uh-huh. Yeah.
or the beginning iterator to another vector, could you use that to copy, remove, or
No, but there's a remove copy that you can also use. So there's a whole pile of different things. We'll talk about some of these algorithms that a remove copy is something you can do to make a copy, and as you're copying, you remove stuff you don't want. Remove is not that, but there is a remove copy. Yes, sir.
So after you use remove,
Yeah.
my ints dot n will still return the same thing.
Yes, that's a really important point. So before we do the erase, if we were to go up here and say myints.end after doing the remove, it doesn't know that it's been changed in any way, shape, or form. That's kind of the point I was making earlier when we were talking about the difference between things you do on a container versus stuff that a generic algorithm can do. A generic algorithm doesn't know anything about the actual container other than what's exposed to it via the iterators to the container. So in particular, the generic algorithm that you look at for remove or RemoveIf, it doesn't know it's a string versus a vector versus a built-in array. So there's no way for it to be able to call something to erase those elements. All it knows is I copied over the stuff you didn't want, sir, and here, now I give it back to you, munged. But the underlying vector, which may have been partly changed, won't have its end changed unless you do erase. So the canonical idiomatic way of handling that is after you do remove or RemoveIf, then go ahead and call erase, and you'll get rid of the items you don't want, if that's what you want to do, obviously. Yeah?
So begin or remove, regular remove will remove a specific value that you input.
Yep.
Remove if.
So regular remove removes a value that you indicate, like if it's an array of a vector of ints, value 20. RemoveIf, like all the if algorithms, and there's a gobs and gobs of if algorithms, those all take predicates, which are basically functors. And so you can give they can do arbitrary things. So in this case, it checked to see whether something was odd as opposed to looking for the value 20. So it's more generalizable. Other questions about that? Okay. So I mentioned before that transform is my all-time favorite STL algorithm. You can do so many cool things with transform. Let's take a look at a simple example here. Hopefully you can kind of see that. So this simple example is going to use transform in order to take all the characters in a string, and any of the characters that are uppercase are going to be replaced with lowercase characters. So it's a lowercase operation. And we do this using transform. So let's take a look at how this works. We start out with a main program, says hello, all capitals. We print that out. We then call lower, which is defined up here, and that takes the original string and that returns a new string. And when we print that string out, what we would find is that it's been lowercased. And the way it works, if you take a look at the lower algorithm, it starts out by calling transform. And this is the 4-parameter version of transform. There's also a 5-parameter version of transform as well. We'll look at that later. So what this does is it starts from the beginning of the string and it goes to the end of the string. And for every element in the string, it's going to call this particular predicate. It's really a functor. It's really calling a functor in this case. And whatever the functor does, it takes the result from the functor and it sticks it at the end of the string we passed in as the second parameter. So let's go ahead and run this example. It's really fun and it illustrates a bunch of kind of cool things. So let me go ahead and put myself in copying mode, so I can grab that guy, stick him over here, and we need to get this guy too. I think we can get rid of almost all of these guys. All right, so let's see, that hopefully will compile. You never know. Nope. Must have missed something. Ah, yeah, let's see. I hate the way that this thing doesn't work on the screen very well. It's hard to see what's going on. There we go. That's better. What didn't it like? It's probably all due to one silly thing. Oh, back inserter. Ah, of course. Forgot to include a header file. Here, hold on a second.
Is it a C++ 11 issue?
No. It's, oh, duh. It's a didn't include the right header file issue. There we go. That should be happier. No, it's happier, but oh, all right, hold on. It would help also if we included string. That should be happier. That's what happens when you cut and paste code without really thinking about it. So hello, hello. Okay, it did what we expected. Let's take a look and see how it works. So this is the interesting one. This is the transform algorithm. Here's transform. And as usual, there's a gazillion of them. Ah, this is so annoying. It's a big morass. Here we go. This is the transform algorithm we were just looking at. What it does is it goes from beginning to end in the range, and for every element, it calls the functor on each element one at a time, and it stores it into the destination. So it looks very, very simple. We'll see that there's a 5-parameter version that we'll look at later that's also not much more complicated to write, but it does very powerful things. So what it's doing is it's going through this range from beginning to end. It's sticking the result at the end of this thing, and every time through, it's calling this toLower functor, and this toLower functor is just a struct with an operator function call that takes a character, one from each element of the range, and if it's uppercase, it goes ahead and it lowercases it. If it's not uppercase, it doesn't do anything, it just passes it back. So that's basically what transform does. And we'll see later you can do all kinds of interesting things with transform because of the way it works. Here's another example of transform. This example, make that a little bigger, starts out, let's see if I can make it big enough to read in the back without squinting too much. So we go ahead and we create a vector of floats that have 5 elements, each starting with a value of 1. We compute a partial sum of those things, and we store it into the vector itself. So now it's going to be the partial sum of those values. And then we go ahead and call transform. This particular version is the 5-parameter version of transform. And what it does is it goes through this range, and then it uses a second range, which in this case happens to be the same vector. So what it's doing is it's multiplying this vector by itself, because we're passing in the multiply functor, and it's storing the results here into the same vector. So it's multiplying a vector by itself and storing it back in place. Yeah?
Just squaring
It's squaring the partial sum. Then we go ahead and write those things out. And then we go ahead and we transform this thing from, this is the four parameter version, which uses a unary functor as opposed to a binary functor, which goes through every element and divides each one by the constant 3. And we'll talk more about this stuff later. These are called binders, and they're forms of adapters. So we take the divides functor, and for every element that's in this range that's been multiplied by itself or squared, we divide it by 3, and then when we're done, we go ahead and write the results out. So let's go ahead and run this thing just for kicks, and we'll see what we get. Hopefully it'll correspond to what I told you. That would be really embarrassing if it did something different. All right, so there's that. And here's this. And we need to put in numeric. That's the guy we need. Hopefully that's all we need. Oops, yeah, that's don't say that's a compiler. That's, oops. It's probably got another header file that, oh, what's, oh, yes, yes. All right. So you can see what it did. It went through there, and it first created a bunch of a partial sum. So it was basically 1, 2, 3, 4, 5. And then it went through and it multiplied everything by itself. So it was 1, 4, 9, 16, 25. And it went through and then divided everything by 3. So those were the results we got. One of the cool things I like about this particular idiom for printing output is it makes it real simple to see the results without doing much. Just cut and paste. And all of a sudden, now you see the results of the partial sum. You see the results of doing the transform operations and so on. OK, so the other thing I wanted to show you, because it's kind of cool, is the 5-parameter version of transform. And this is called transform 2. It probably is actually faster to look for it here than to try to click around on it. Maybe. There we go. There it is. So here's the 5-parameter version. What you can see it does is it walks through an initial range from beginning to end, and you give it a second range, which could be the same thing or not. It's up to you. And you give it a binary functor, and it calls the binary functor with the first and the second ranges as you march through them, and it puts the results into the destination. And those operations, that simple syntax that you see there, is useful for all kinds of crazy things. We'll come back and look at some other more interesting examples later when we get further along in the course. Yeah?
What does the output iterator do in this transform 5 argument?
All it does is the same thing it does in the 4-parameter version. It just becomes the place you store the results. So it's almost like copy. So in a sense, this is almost like a copy. In fact, it looks almost identical to copy. The difference being every step along the way, you're calling this functor that can transform the data so that what gets stuck into the result, the output iterator, has been transformed from the input. And that's why it's so powerful. OK. The next example, we've kind of seen this already. This is the for each algorithm. As you can see here, this example, we create a little functor. This goes back to the question that had been asked earlier, is are functors more useful than functions? And here's a good example where they're useful. Yes, sir?
What did you say that bind to?
Bind to end. So we'll cover that in more detail. I will show you real quick just to answer the question, because it's a very good question. This is something that's called a function adapter. There are 3 main categories of adapters. You're not responsible for knowing them for the quiz, by the way. We'll cover them later, or probably on Wednesday. The 3 main kinds of adapters are iterator adapters. Back inserter is an iterator adapter. That's something that takes an object that's not an iterator, like a container or an IO stream, and makes it work like an iterator. That's an iterator adapter. There's container adapters, which are used to take containers like dec and vector that have certain behavior and certain interfaces and adapt them to work for other things like stacks and queues. Those are container adapters. And the third kind of adapter is a function adapter, and there's a bunch of them. Binder is a function adapter. What it does in this particular case, bind second, is it takes its first parameter, which is a binary functor, and it binds its second parameter, hence bind second, to a constant. And so you can now use this binary functor, like divides, in a context that's expecting a unary functor. And the reason for doing these adapters is that way we don't have to write a whole separate set of functors that do things like divide by const or something like that, right? We can use the generic binary functor and simply bind it to a constant. So you'll see adapters are used throughout STL. We'll cover these more in a little bit more detail later, but basically it allows us to be able to take existing code and then make it work in a slightly different context without changing the existing code. Very powerful technique. So here's an example of the for each algorithm. As you can see here, we're going to have a built-in array. We do our little SizeOf trick we looked at before. And then we call for each. And what we're going to do here is for every element in this range, we're going to print it to some output. Now, again, we could use copy for this. I'm just illustrating the use of for each for the same case. Yeah, Patrick?
For each transform differ.
In a number of different ways. The main difference is that transform actually modifies its output iterator. So there's an output iterator that's passed to transform. For each, there's no modification of the underlying data structure. So it just basically calls a method on every element, but it doesn't transform it, doesn't change it. So what we do here, as you can see, is for each element, we go ahead and print it out. And this illustrates some interesting things. So notice that the print functor has a constructor that stashes away the output stream where we want to write the output. So it would be trivial to replace cout with cerr or a file or something else. So that's easy to do. And we also keep track of the count, which we stash away as a local variable. This comes back to the earlier question, how does a functor differ from a function? So a functor, since it's a class or a struct, can store state. It can also have constructors and other methods. So what this does is every time its operator function call is invoked, every time through the loop, it goes ahead and outputs to the O stream that it's stashed away, and it also increments the count by 1. And so when we're all done, it'll print out a bunch of things, and it'll also give you back the functor, which you can then use to keep track of some state that may have occurred while you were in the midst of doing the iteration and calling the operator function call. So it's a really cool example of where you pass in an object by value, which, as you can see in this case, is actually an anonymous object, right? Print is an anonymous object. That gets used every time through the for each loop. And when it's done, it returns by value the updated functor that was originally passed in. We grab that guy here, and then we go ahead and write the output there. So for each is a very powerful way of iterating through something and keeping track of whatever it does along the way, if that's what you want to do. Now, there's lots of other ways to do this in C++. You can use, you can write range-based for loops. You can use lambda expressions. You can do other kinds of things. For each is just an algorithm that kind of bundles it all up in one place. Yeah? So transform. I don't think transform returns anything, and that's because it modifies the output parameter, the output iterator that's passed to it. OK. So we're now essentially done with algorithms. There's lots and lots more algorithms, by the way, which we won't probably cover in great detail here. STL has hundreds of algorithms at this point, and there's many more in Boost, which is kind of the proving ground for STL advances. So you could learn STL algorithms till they came out of your ears. But that's not really what we're trying to do. We're trying to give you the essence of the key things, some of the key algorithms that we're going to talk about, some of the things we'll use later. So what we're going to do next time, in addition to having a quiz, take any questions you have on the programming assignment, make sure you're working away on that to get it done on time. And then we'll also focus on functors and adapters. And I don't think we're going to wrap all of STL up by Wednesday, but we should wrap it all up by Monday. And that'll give us a chance to start focusing on the next part of the class, which is really the cool part, which is patterns. OK, questions, comments? See you Wednesday.